Hello, I am the Mighty Pez. In this, the second part of the introduction to my simple Z80 breadboard computer, I will demonstrate the process of hand coding, hand assembling, and then manually loading and running a trivial Z80 assembler program. So please join me. As my breadboard computer does not yet have any I/O support, I cannot yet persistently store nor load any significant programs such as a compiler. Therefore, anything I want to do with the computer at this state must be done manually. For this demo, I will write a simple program using Z80 assembler instructions. The program will perform a loop 5 times and then halt the running program. Next, I will convert or assemble the instruction mnemonics, again by hand, into Z80 machine opcodes. Then convert the hexadecimal opcodes into 8-bit binary numbers in order to be loaded into the MP80 and then executed. So off to the right you can see a simple flowchart of the program that we are going to code. We're just going to follow that flowchart. We're going to start out with a no op that is not required. I'm just putting it in here for my visibility. We're going to load the value of 5 into the B register. We're going to add a target label. This will be for the loop that we write. Then we're going to add another superfluous no op, again just for my visibility while running the program. Next we're going to use an opcode called decrement and jump if not 0, DJNZ. It decrements the value of the B register, and as long as the value is not 0, it will continue to loop. As soon as we hit 0, then it will pass on to the next instruction, which will be a halt command. And that is the entirety of our program. Next we will look at hand assembling this code. I've gone ahead and printed the assembler code out that I previously wrote. And I will be using this Z80 reference card to convert the instructions into opcodes. Although the Z80 has multi-byte opcodes, our minimal program relies solely on single-byte opcodes for now. You can see that each of our program instructions consists of 2 hex-digit opcodes, with the most significant digit in the left column and the least significant digit on the top row. For example, the no op instruction is found in the upper left cell of the reference chart and would match up to opcode 00. So beginning our assembly process, we will use opcode 00 as our first instruction to be loaded into address 0. For address 1, we will locate the instruction load B, which is used to load data into the B register. We find this instruction at opcode 06. Address 2 will be the second part of the instruction and is the data to be loaded into the register, the value 05 hex. I will denote the label as a target before instruction 3, as a label is just a target address and does not take up any actual instruction space in the generated code. Address number 3 is our second no op and will again be written as opcode digit 00. Address number 4 is the decrement and jump if not 0 instruction, which we find at opcode 10 hex. The next value for address number 5, the target of the jump, will have to be calculated. The value of the jump is not a direct address, so we can't jump directly to address number 3. This instruction performs a relative jump up to 128 locations, either forward or backward. We will be jumping from a starting location of the program counter after the result of processing the 2-byte instruction. This means, for our purposes, we will be starting our jump from the program counter value of 6. So to get back to address 3, we will begin at address 6 and make a jump of -3 addresses. To calculate a negative value, all we have to know is that 00 hex minus 1 is FF, and continue from there. 00 hex minus 2 is FE, and 00 minus 3 is our desired value of Frank delta hex. And our last opcode is for the halt instruction and is found at opcode 76 hex. Since this computer does not support hex data entry, we must now go through the manual conversion step of converting hex to binary. The key is that each hex digit is one 4-bit nibble, so we just convert each half of the opcode, or data byte, into 2 4-bit segments per address. We know that there are 7 total addresses we need to fill, 0 through 6. The no-ops are simple. 2 4-bit zeros, nothing to calculate. 06 hex is a 4-bit 0, followed in the second nibble by a 0 in the 8's place, 1 in the 4's place, 1 in the 2's place, and 0 in the 1's place. 05 hex is a 4-bit 0, followed by a 0 in the 8th place, 1 in the 4's place, 0 in the 2's place, and 1 in the 1's place. Address 3 is another 8-bit 0 no-op. Address 4 is a 1 in the most significant nibble, followed by a 0 in the least significant nibble. Address 5, Frank delta, has 1s in the most significant nibble and 1, 1, 0, 1 in the least significant. And finally, address 6, the 7th address by count, but addressing is 0-based, is 0, 1, 1, 1 in the most significant nibble, and 0, 1, 1, 0 in the least significant. And now we've completed the coding of our trivial example in Z80 assembler, converted the assembler code to Z80 hex opcodes and data, and then for our machine converted the data into binary to be hand-loaded into the MP80. And now we are ready for the demonstration of loading and running our hand-assembled program. We start from a default front panel setting with all 3 switches in the off position. The memory function is set to exam mode, device control set to manual mode, and clock set to manual mode. To manually load memory, we switch the memory function mode to store, reset the address counter to 0, and clear the data register. Then we start by entering a 0 byte into memory, pressing the load increment button, followed by entering the remaining 6 bytes into memory. I go ahead and add several superfluous no-ops at the end of the program. Not necessary, but I prefer that there is no random data at the very end of my program. I set the memory function back to exam mode so that all switches are in the off position, the default state. We are now ready to run, so I put the clock into automatic run mode and then enable CPU control. We can now watch the data and the address bus as well as the halt light, and keep a specific eye out for the pattern of Frank delta, which is 7 ones except a 0 in the 2's position. You will see that this pattern occurs 5 times before it passes out of the loop. The halt light will go low several clock cycles after the 5th occurrence of the FD hex pattern, indicating that the processor has stopped reading and executing instructions from memory. The CPU itself is still active doing housekeeping, such as looking for interrupts to occur. Since I've not designed any support for interrupt handling, it will take putting the system into manual mode to drive the reset line active low in order to reset the halt state. With the first phase of my breadboard computer completed, I will next evaluate solutions for serial input-output, storage, and an EEPROM-based monitor program. Thank you for watching.